Hello, and welcome to Ohio DOT's training for its Multimodal Design Guide, or the MDG. This video is the third module of a 13-part training series that will span the entirety of the guide. In this video, we'll focus on Chapter 3, Elements of Design. This chapter provides guidance for elements of design that are common to a wide range of pedestrian and bicycle facility types. These topics and design elements include design speed, sight distance, physical and operating widths, geometric alignments, and other considerations such as utilities, landscaping, and surface treatments that may be universal to a wide variety of treatments. The preface in the L&D Manual Volume 1 states that designers must understand the context and the constraints of their project when selecting design criteria. L&D Manual Volume 1 describes the performance-based project development strategy that, like the AASHTO Green Book, highlights the need to establish a purpose and need for a project, and then evaluate options and design deviations that meet the project purpose and need. The MDG notes that design flexibility should be used to prioritize the safety, comfort, and connectivity of people walking and biking, and that proposed project improvements should be targeted and right-sized based on project-specific needs, which may be identified in the project's purpose and need statement. When applying design flexibility, it is important to follow and document the clear process that was used to determine the appropriate application of or deviations from design guidance in order to achieve the appropriate solution. When implementing design decisions that are within the range of allowable values, but that perhaps use a higher value than the minimum values, these decisions should also be documented. All relevant design information, such as the selection of design user, design width that's selected, and others, should be documented in the project file. When discussing user profiles for pedestrians, it's first important to remember that everyone is a pedestrian at some point in their day. Designers should understand that pedestrians display a wide range of physical, cognitive, and sensory abilities. If a design works well for people with disabilities, it generally works well for those who do not have disabilities. As an example, a person pushing a stroller or making a delivery with a wheeled dolly will rely on or benefit from accessible designs such as curb ramps. It's also important to remember that disabilities are not a special condition of the few, but are ordinary occurrences that affect most people for at least some part of their lives. Many people sprain an ankle or break a leg at some point and cannot traverse stairs or may find difficulty at curbs or street crossings. In addition to disabilities, age is one of the major factors that can affect a pedestrian's physical characteristics, walking speed, and environmental perceptions or reaction times. When facilities are designed for people of all ages and abilities, the transportation network can begin to safely and conveniently get everyone where they need to go. The user profile for bicyclists, of which there are 3, depends on the context of a project area and may affect which users we're designing for. Typically, in built-up areas, our design user is the interested but concerned bicyclist, noting that when we design for the interested but concerned bicyclist, we design for everyone. The reverse is not true. In rural context, our design user is typically the highly confident bicyclist. These are the default assumptions, but may differ depending on your project location. For example, in a rural area connecting residential to a school, you may be designing for the interested but concerned bicyclist. Designers should also understand that a person's design profile, as either a pedestrian or bicyclist, may change throughout the day. For example, a person who walks or bikes to work may be more confident or comfortable using a large arterial street with standard width sidewalks or standard width bike lanes. That's when they're traveling alone. But when they're traveling with their children, they may prefer to use lower volume or lower speed streets that have wider buffers from traffic, wider sidewalks, or a shared use path. Section 3.2 discusses the performance characteristics of the typical adult bicyclist, who should generally be used to establish many of the geometric design controls because adult bicyclists are typically the fastest and largest users. The guide table shown on this slide summarizes typical features or characteristics that may impact bicycling, such as acceleration, deceleration, and reaction times. These values are incorporated into other equations throughout the MDG, such as guidance for sight distance and signal timing. The use of these values will generally ensure that bicyclists of all ages and abilities are accommodated on bikeways and roadways. That said, the context and expected use of the bikeway and the roadways should also inform design decisions. For example, a shared use path that's expected to have low pedestrian activity and anticipated to be used for recreational bicycling may be a location where higher bicyclist design speeds are appropriate and should be designed for. Typical variations in height, width, and the length of a variety of mobility devices are shown on this slide for both pedestrians and bicyclists. Although recommended facility widths for bike lanes, shared use paths, and sidewalks in the MDG generally accommodates these devices, designers should be cognizant of the expected use of the longest or widest devices and should provide appropriate accommodations for these uses when they're expected. For example, the typical design vehicle for a shared use path will often be the adult bicyclists. But when we're designing a shared use path, we may expect higher percentages of people bicycling with a trailer and need to be cognizant of this at trail crossings, ensuring that a wider pedestrian refuge is provided to accommodate the longest vehicle. Pedestrian design speeds are primarily used for determining pedestrian clearance intervals at signalized intersections, but are also used for determining sight distances at some uncontrolled crossings if pedestrians are looking for gaps in traffic. Pedestrian speeds can vary based on physical ability, mobility device used, age, trip purpose, and in most cases will range from 1 to 4 feet per second. 3.5 feet per second is the default assumed pedestrian design speed under most circumstances. Designers should consider are seniors and children present, and those users typically walk slower at around 3 feet per second. As such, that preferred user profile may be appropriate for assessing street crossings. A crossing that accommodates these lower users will naturally accommodate the faster users. The use of mobility devices can also affect walking speeds, and speeds can vary for people with disabilities, as shown in the table on this slide. Designers should consider the frequency of users with mobility devices and disabilities and adjust design speeds accordingly. The MDG also mentions the speed of joggers at 7.5 feet per second. This will be relevant for assessing sight distances, particularly between bicyclists and joggers at intersections of shared use paths. There is no one-size-fits-all design speed for bicyclists and micromobility users. The MDG provides information on the things designers need to consider, provides recommended speeds and ranges, provides information on dealing with areas where speed changes occur, and provides acceleration and deceleration information. Separated bike lanes and most shared use paths will use a design speed of 15 miles an hour. This is still higher than the typical interested but concerned bicyclist. Low volume shared use paths may function as bicycle highways for long distance travel with few conflicts, so a higher design speed may be appropriate. Bike boulevards en- encourage a design speed that is similar for both bicyclists and motorists. So the target speed for these facilities is in the 15 to 20 mile per hour range. The MDG does include reference to e-bikes, but not a lot of research is provided on them at this point. As planners and designers, we need to pay attention to increases in top speed, but this doesn't mean that we have to design facilities to assume the top speed of these vehicles. There are three key factors that should be considered when designing interactions between bicyclists, motorists, and pedestrians. Number one, motorists and bicyclists have a legal responsibility to yield to pedestrians in crosswalks. Number two, pedestrians cannot suddenly leave the curb if vehicles are too close to stop. And number three, motorists and bicyclists must exercise due care to avoid colliding with pedestrians and other motorists or bicyclists. The result is a mutual yielding responsibility among motorists, bicyclists, and pedestrians, depending on the timing of their arrival at an intersection. This may also be referred to as opportunities for mutual identification. These are pieces of the law that help to inform how separated bike lanes should operate, since they are more unique than conventional travel lanes. But these principles also hold true at shared use path crossings where pedestrians have the right of way, but can't exercise that right if a motorist is too close to stop. The effectiveness of mutual yielding is dependent on the ability of each user to see and react to each other, which relies upon providing clear sight lines between the relevant users, the use of appropriate traffic controls to communicate the right of way, and sufficient lighting for everyone to see each other. Let's break down the graphic on the slide. The first zone when approaching an intersection is the recognition zone. In this zone, an approaching user has an opportunity to see the other user and evaluate their respective approach speeds based on their position. The condition on the left shows a situation where a bicyclist is ahead of a motorist, whereas the condition on the right when a motorist is ahead of a bicyclist within the recognition zone. Sightlines must be preserved in the recognition zone as demonstrated in the graphic to allow the trailing user to see the person ahead of them. The next zone when approaching an intersection is the decision zone. In the decision zone, the bicyclist, motorist, or pedestrian uses the information obtained in the recognition zone to identify who is likely to arrive at the intersection first and adjust their speed to either yield or stop as appropriate. The final zone at an intersection approach is the yield zone. The yield zone is where the bicyclist, the motorist, or the pedestrian yields or stops as necessary to avoid a conflict. Communicating who has the right of way at an intersection is a very important traffic engineering concept. Bicyclists, pedestrians, and motorists should be provided with the cues and treatments that both clearly establish which user has the right of way and consistently communicates expected behavior. Among some of the ways that designers can communicate right-of-way priority includes marking crosswalks at shared use paths, marking bicycle crossings of roadways, marking pedestrian crossings of bicycle facilities, providing audible and tactile devices for people with disabilities where they're appropriate, placing regulatory or warning signs for crossing, merging, or turning traffic where it's appropriate, and finally, signalizing where that's appropriate. Section 3.5 of the guide covers sight distances. 8 different sight distances are provided, labeled as case A through case F. These sight distances rely heavily on stopping sight distance for bikes, so that should be evaluated when assessing sight distance. Equations and assumptions are provided so they can be adjusted if needed for specific circumstances. Of note, horizontal sightline offset is a feature really only seen on shared use paths. As such, that sightline is only provided in the shared use path chapter of the MTG. Next, we'll walk through the various bike cases. Bike case A is applicable to both side paths and separated bike lanes, and it's unique among all the sight distance guidance. The challenge is that you have two vehicles moving in the same direction at different speeds. There is no comparable sight distance for motorist to motorist interactions in the AASHTO Green Book. Bike case A reinforces the importance of mutual yielding and relies on the principle that the person who will arrive at the intersection first has the right of way, and that each user needs to see the other user in order for this principle to work. Unlike other sight distances in the guide, this shows approach clear space rather than a sight triangle. The provision of the noted approach clear space, free of sight obstructions like trees or on-street parking, and based on the intersection design characteristics of effective turning radius, are fundamental to how bike case A works. As such, this relies on the expected turning speed of a motorist based on the effective turning radius of that motorist. If a car can turn fast around a large intersection corner, then they won't be slowing as much as they approach a typical intersection. This would then require more approach clear space. By contrast, if you provide a small effective turning radius at an intersection, then you end up needing less clear space on the approach because that motorist is already slowing to a lower speed at the intersection. Next up is bike case B. This case applies when a motorist is making a permissive left turn at a traffic signal or from an uncontrolled approach and will cross a two-way bikeway. For example, a left turn from an arterial onto a local street or driveway crossing of a two-way separated bike lane or side path. On one-way streets, you will have similar operating dynamics and approach clear space requirements for bike case A will apply since motorists will be turning adjacent to the separated bike lane. On two-way streets, there are two sight lines that should be maintained. A left-turning motorist approaching a turn needs a line of sight to bicyclists approaching from the same direction as was shown on this screen. On streets with two-way traffic flow, the operational dynamic of a motorist looking for gaps in traffic creates unique challenges that cannot be resolved through improving sight distances. This is a challenging maneuver because the motorist is primarily looking for gaps in oncoming motor vehicle traffic and is less likely to scan for bicyclists approaching from behind. Unlike for bike case A or bike case B on one-way streets, where the motorist is decelerating towards the crossing, the motorist in this case may be accelerating towards the crossing once they perceive a gap in traffic. Where there are high volumes of bicyclists or turning motorists, or multiple travel lanes to cross or high operating speeds, in those cases, signal separation should instead be considered to address this conflict. All bike case Cs are for scenarios where a motorist crosses a separated bike lane or a side path and is similar to the ideas presented in the AASHTO guide for the development of bicycle facilities, where a motorist crosses a bike lane or a mid-block path. Bike case C1 applies when a motorist crosses a near-side separated bike lane or side path before continuing straight or turning at that intersection. There are two scenarios for this crossing, a two-step or a single crossing. In the two-step, motorists assess the bikeway conflicts, then they move forward. So designers will check the bike case C1 sight distance, then they will check AASHTO Green Book case B for each separate location. Two things of note here. When a motorist moves forward, it's possible, or likely, depending on the width of the street buffer, that the motorist may block the bike lane as they wait to assess motor vehicle conflicts. Second of note, while bike case C1 sight triangles are the recommended sight distance for the visibility of bicyclists, the minimum requirement for any intersection is to at least provide stopping sight distance for the bikeway. This provides sufficient time for the bicyclist to exercise due care to slow or stop for a crossing motorist that's already within the intersection. In the single crossing scenario, a motorist assesses both the bikeway conflict and the motor vehicle conflict from one stopped location. Then they perform their turning movement when there is a sufficient gap in both the bikeway and the motor vehicle traffic. This scenario might be appropriate in locations where the motorist would otherwise block the bike lane for extended periods of time, or where bicycle volumes or motorist volumes are anticipated to be high. Note, you'll need to assess the L&D sight distance to account for a wider crossing than just the travel lane. The L&D gives guidance on wider road crossings. Bike case C2 applies when a motorist crosses a far side separated bike lane or side path. When the motorist approach is stop controlled and the bikeway crossing is uncontrolled, the intersection sight distance described in the L&D Manual Volume 1, Section 201.3.2.3 should be used to calculate the departure sight triangle between the motorist and the intersecting bikeway. As with bike case B, this case creates challenging dynamics that are often difficult to resolve by increasing the size of your sight triangle. In urban areas, it may be difficult to increase the sight triangle enough to provide intersection sight distance to judge gaps with all conflicting traffic and allow a motorist to cross all the travel lanes as well as the separated bike lane or side path on the opposite side of the street. As such, designers should consider the frequency of through movements at these types of intersections and provide either traffic control devices or adequate sight distance, i.e. minimum stopping sight distance, for bicyclists to see and react to a crossing vehicle and stop if necessary. It may be appropriate to restrict these through movements for motorists where traffic control devices or sufficient sight distances cannot accommodate this sight line. Bike case D describes where a stop-controlled roadway intersects an uncontrolled roadway. Because a bicyclist on the stop-controlled roadway does not have the right-of-way, they must judge the speed of and gaps in approaching motor vehicle traffic from their location at the edge of the roadway to determine when they will have sufficient time to cross. Providing the minimum stopping sight distance for the motorist on the uncontrolled roadway approach will allow the motorist sufficient time to exercise due care to stop or slow for the crossing bicyclist who may still be within the intersection. If a shared use path intersects another shared use path and the intersection is uncontrolled, sight triangles similar to the yield condition described in bike case E above should be provided. However, both legs of the sight triangle should be based on the stopping sight distance of each shared use path user. Where clear sight lines cannot be provided, it will be necessary to provide some traffic control to communicate the right-of-way. And finally, at the intersection of stop-controlled shared use paths and walkways, a clear sight triangle extending at least 15 feet along the walkway and 25 feet along the shared use path should be provided to ensure clear sight lines between the path and walkway users. At an intersection of a walkway and an uncontrolled shared use path, or where pedestrians cross a separated bike lane, the length of the clear sight triangle along the bikeway should be determined using the equation presented in the MDG. You'll find that in table 3-12. Or you have to provide the minimum stopping sight distance, whichever is smaller. If pedestrian crossings of bikeways are unexpected, signs may also be appropriate to warn bicyclists of that pedestrian crossing. In addition to establishing the user profile and performance characteristics of people walking and bicycling, designers should understand the principles of operating space for both sidewalks and bikeway users. When developing design parameters for sidewalk and bikeway widths, designers should consider the space occupied by the user and whatever device they may be using, their operating space, i.e. the natural side-to-side movement of that user, and any additional shy spaces to vertical objects or obstructions adjacent to the walkway or bikeway. For the purposes of defining typical physical space dimensions, a typical adult in a wheelchair should be assumed as the pedestrian. A person in a wheelchair's physical space is typically 3 feet wide by 4 foot long. Keep in mind, this is just that physical space and that additional space is needed for a person operating a mobility device or walking. Next, we'll discuss the user operating space and facility width. This is not to be confused with the design user profile, which we previously discussed as a level of comfort. The bicyclist design user is an adult bicyclist with a couple of exceptions. Number one, the height of the bicyclist is usually the recumbent bicyclist or a child bicyclist for the purposes of establishing sight distance. Crossing speeds typically use the crossing speed of a pedestrian if bicyclists and pedestrians will cross together. And finally, as we previously discussed, median widths should accommodate the longest vehicle, which may often be the bicyclist with a trailer requiring 10 feet as opposed to the 6 feet. It's important to understand the physical and operating spaces needed by bicyclists when determining how facility widths will affect those users. Each of these spaces are essential to a bicyclist's safety and comfort and are accounted for in the tables describing minimum facility widths throughout the MDG. While there may be instances where constrained widths are okay, they should not be used as the default as they reduce or eliminate some of the needed space to safely bicycle. Bicyclists have the potential to collide with physical objects such as walls, fences, or curbs, or into other bicyclists or pedestrians on shared use paths. If sufficient shy distances are not provided, bicyclists may have the potential to collide with physical objects such as walls, fences, or curbs, or into other bicyclists or pedestrians on a shared use path. The MDG provides both minimum and constrained shy spaces and bikeway widths. In later chapters, you will see bikeway widths that depend on their proximity to curbing or other vertical objects. This is to account for the bicyclist shy space that's typical for that particular design element. Although the recommended bike widths in the guide typically consider proximity to vertical objects, an understanding of shy space will help all designers to understand how a bikeway is likely to operate or understand the operating space of that bikeway. As an example, this consideration of bikeway width and shy distance is particularly important for bikeways on bridges, where shy space along a bridge parapet or concrete barrier can limit the operating width of that bikeway. On a constrained bikeway width, riders must generally operate single file and can only occasionally pass a slower bicyclist. During a passing maneuver, there is a higher crash potential between these bicyclists because of the limited operating space provided. Narrow bikeways therefore force single file operation or slow speed passing, which precludes opportunities for social cycling. This is what that condition looks like. When the low end of the minimum widths are provided, passing may still be accommodated because the bicyclist operating space is essentially limited to their physical width and the two bicyclists are only located side by side for a few moments. By comparison, wider bikeways account for the natural user behavior, including both side-by-side riding and more frequent passing. They have a greater capacity to accommodate a higher volume of users, as well as wider bicycles such as delivery tricycles or cargo bikes, while allowing for that social cycling experience. Wider bikeways account for that natural user behavior, including side-by-side riding. As shown here, sufficient width will accommodate side-by-side riding and provide greater capacity to accommodate those higher volumes of users. Next, we'll discuss horizontal alignments and tapers. For on-street bike facilities, basic horizontal geometry for motor vehicles will result in a facility that generally accommodates bicyclists and pedestrians. Guidelines for the horizontal alignment of a shared use path that deviates from the roadway alignment will be discussed in the shared use path chapter. There are a few additional topics in chapter 3 of the guide which we are not covering in this training. Those include cross slope, vertical alignment, utilities, lighting, drainage, landscaping, and surface conditions. Please see the MDG for these topics. Thank you for watching this video covering chapter 3 of the MDG. For other chapters, please see the other videos in this series.